Here we have the 2014 Senior External Physics Exam in Queensland. We're looking at Paper 1, Part A, Section 1, Short Response, Question 6. The first thing we do is we read the question carefully. A two-point light source interference experiment used to determine the wavelength of monochromatic light source has a screen placed 4.2 meters away. If the slits have a 5.00 by 10 to the negative 5 meters separation and the dark fringes on the screen have a uniform 2.80 centimeters separation, what is the wavelength of the light source? Okay, we've read the question and understand it. Let's go back now and identify the important pieces of information. Okay, it's a two-point light source interference experiment. We're looking for wavelength of monochromatic light, and we've got a screen placed 4.2 meters away. Let's highlight the 4.2 meters. The slits have a separation of 5 by 10 to the negative 5 meters. That's good. Both of our measurements so far are in meters. And the dark fringes on the screen have a uniform 2.80 centimeters separation. We've got a measurement here in centimeters that we will need to transfer into meters, so we're consistent with our SI units. We want to know the wavelength of the light source. Right, we need to draw a diagram. Let's draw the diagram. We've got a two-point light source, and so we have a gap, and we have a gap that light shines through, and so here is our light source. Our light source goes through these two slits, and we have a screen here, and our screen is 4.20 meters away. That is our length of 4.20 meters. The slits have a separation of 5.00 by 10 to the negative 5, so 5.00 by 10 to the negative 5. That's the separation of our slits, so we call that distance D. And we have dark fringes on our screen. So we start off with a central maximum, and then we have a dark fringe, which is our first minima, and we have a dark fringe, which is our first minima. Then we have our first maxima, then we have our second minima. On the other side of our central maxima, we have our first minima, and then we have our second maxima, and then our second minima, like so. So there's our series of dark bands. The dark bands are 2.80 centimeters, 2.80 centimeters apart. That is our delta X value, our separation of our slits. That's in centimeters. Okay, so we've actually drawn our diagram. Now we need to decide how to go about solving this particular question. In order to make that decision, let's make sure we've got all of our measurements written down. 5.00 by 10 to the negative 5. That's in meters. Our length is in meters. Our separation of our slits is in centimeters, so we need to multiply that by 10 to the negative 2 to get it into meters. So I've got meters, meters, and meters. And from that, I'm after lambda, a wavelength is our unknown. So we need to have a look at our formula sheet if we're going to decide how to actually go about solving this particular problem. We know that our formula sheet starts in kinematics. We're doing the light section. So the light section is our second lot of formula. We look for our formula here, and the values that we're after in our formula are D, L, delta, X, and lambda. Here's the formula here that has D, L, delta, X, and lambda. So we transpose that from here onto our solution sheet. Delta X equals L lambda on D. Okay, so we've decided how we're actually going to go about and solve this particular problem. We need to lock in our values, but we need to have lambda as the focus of our equation. So we need lambda. To get lambda by itself, divide both sides by L. So we get delta X on L. The L's on this side cancel out. To get rid of the D, we multiply both sides by D, and the D's will cancel out. So our formula becomes delta X, the separation of our slits, the separation of our dark fringes, D, the separation of our slits, divided by L, which is the distance away to our screen. Let's put those values in. Delta X, 2.80 by 10 to the negative 2. multiplied by D, 5.00 by 10 to the negative 5, and divided by 4.20. They're all in metres, so we now need to put those values straight into our calculator. 2.8 times 5 divided by 4.2 equals 3.3333 continuous. We need to decide here how many of those threes we're actually going to include, but now let's work out our indices. On our top line, 10 to the negative 2 and 10 to the negative 5. If we add our indices, that gives a total of 3.33 by 10 to the negative 7. To work out how many significant figures to use in our answer, we need to have a look at the information that we're provided. 4.20 is 3 significant figures. 2.8 is 3 significant figures. 2.80 is 3 significant figures. And 5.00 is 3 significant figures. So all of our information is provided as 3 significant figures. So we need to give our answer to 3 significant figures as well. And our unit is in metres. So we've gone through now and we've done the evaluation. Let's see whether our answer makes sense and we've got our significant figures right. So what is the wavelength of the light source? So we need to include the question as part of our answer, and we say the wavelength of the light source is lambda 3.33 by 10 to the negative 7 metres. 3 significant figures in our answer, 3 significant figures in all of the information that's given to us. When we're looking at the marking scheme, this question is worth 3 marks. You get 1 mark for getting the formula with lambda, the wavelength, being the focus of the formula. You get 1 mark for substituting in all of these values correctly, and then you get 1 mark for actually calculating the answer to the correct number of significant figures.